So hi guys, so we've been studying a whole lot of curves in calculus and of course in our algebra course, and we're going to be looking at something called parametric curves today. Parametric curves. Something very interesting. We think of a curve like y equal to x squared. It's a function of how many variables? Just one variable. So as x varies, it'll generate the y values and we can plot y equal to x squared is just a parabola. Okay? Then we can also have functions of two variables. So that will give you what we call a surface plot. But that's not too important for us just yet, not part of this syllabus at all. But then we have a situation where our x values and y values, just say if you're looking at, okay, let's look at y equal to x squared. But x is a function of, say, t. Now this is interesting because if you look at motion of an object, then you'd find that the x-coordinate changes with time. And that will now give you an output. So we have the x and y connected to some variable, or what we call some parameter. And usually in physics and engineering, that parameter is the time coordinate. So let's have a look at some of these curves, which we refer to as parametric curves. Now have a look at this path or trajectory, if you could say, taken by some object. It could be a flying or buzzing bee, and as it moves around through space, it starts off at t equal to 0. We have a stopwatch and then we time it. 15 seconds later, we plot its path through the atmosphere, say, and it gives you that blue curve. That's extremely difficult to put a formula to that curve. For instance, y equal to sine x. It's not, okay? One could do some sort of approximation, but that ain't going to help us at all. But what we realize is the coordinate x and y both depend on a third parameter, and that's what we would call t. And in a real case scenario, a flying bee, and we want to look at its position in space, then that coordinate would be the time coordinate. So the t is what we call the parametric curve. Now let's have a look at some simple parametric curves before we start doing some elegant things with it, like differentiating a parametric function. Equation, you've got x equal to t squared minus 2t, and y is equal to t plus 1. So x and y, if you look at it very carefully, we are so used to writing y as a function of x, and now we've got them as functions of t. So is it possible to actually write y as a function of x? And that is maybe, for instance, solve for t here. So if I have a look very carefully, I just want to show you something very quickly. So t is y minus 1. And what if we substitute that in there? So I'll get y minus 1 squared minus 2. And then t is y minus 1. So square that out very quickly. Y squared minus 2y plus 1 minus 2y plus 2. And eventually what we get is x equal to, well, there's my y squared. Minus 2y is minus 4y. And 2 plus 1 is 3. Haha, you'd say, hey, that is quadratic in y, so that looks like a parabola. Interesting, yeah, so it does look like a parabola. It doesn't seem like from the original curve in terms of t, but once we eliminate t, we can see it looks like a parabola, but not in the usual standard position. And that's interesting. But if we had to plot this curve, why not choose values for t? So let's, for example, if I choose t equal to 0, then what is y? Y would be 0 plus 1, which is 1. The corresponding x value would be 0. So at t equal to 0, x is 0, y is 1. And you continue choosing these values, and you will generate a curve. So let's see what that curve looks like. Okay, so there's the table there, and notice when t is equal to 0, we said y was 1, x was 0, and then we start to plot this curve for different values of t. And it's interesting to have a look. We know it's the parabola because we eliminated t. We knew it's a parabola. I stated it wasn't in the standard position. It was x as a function of y. And so you had this type of symmetry over here. But what's interesting about this curve is the sense. There's a sense of direction over here. And you can pick out that sense very quickly as the t values start to progress. So I want you to spend 30 seconds just having a look at this and agreeing with me that the direction of the arrows or the sense of that curve is in that form depicted over here as you see those arrowheads. The clue again, I said, refer to the table, think of t as time, you have a stopwatch, and you are generating this trajectory or path of a particle where x and y are both functions of time. Haha, sweet curve this. What curve is represented by the following parametric equations? Now again, I mean, x equal to cos t, y equal to sine t. You know, you look at face values, I don't know what this is. I mean, I've never seen this before. But have a look here and something sweet really happens. And you don't have to do this all the time if you want to plot these curves. You've got x squared is equal to cos squared t, y squared is equal to sine squared t. And guess what? If I add those things, I'm going to x squared plus y squared is cos squared t plus sine squared t, and that gives you 1. So we know, we've seen this in grade 11, for instance, that x squared plus y squared equals to 1 is an equation of a circle radius 1. Yeah, that is so cool. And there's the equation that, that's the circle that you see for the curve x equal to cos t, y equal to sine t, defined parametrically, or x squared plus y squared equals to r squared. Now again, have a look at that pink curve. There's a sense of direction. Watch the arrows. Do you agree with that? So from 0 to 2 pi, you remember 0 to 2 pi, 0 to 360, those, if you think about the trajectory or the path, that should cover a complete circle, one revolution. But do you agree that the sense or direction of it is anti-clockwise? And why is it not clockwise? It's anti-clockwise. Again, 30 seconds off, pause the video, breathe, have a look at the curve, and tell me whether you agree with the sense of direction. Hint, hint, take different values of t, have a look at how cos t, sine t evolves with different values of t, and that should give you the sense of the direction. All right, so one of the very important things here is what we call differentiation of parametric curves. So if a curve is defined parametrically, then we must be able to differentiate. And this is very, very important, especially later on when one looks at what we call the arc length. So for instance, you're traveling on this weird path and you want to work out, say, the length of that path. How do you work that out? And that's going to be related to what we call the distance formula, or the formula in terms of the length. This is extremely important in physics. I mean, I watched a beautiful video the other day, and that involved a car skidding along the road. And the car skids along the road. It doesn't skid along in a perfectly straight line. The path is curved, and it's not a perfect sine curve or cos curve. And you could use a piece of string to calculate it, but is it possible to put a function to define it parametrically so that you can do some interesting things, like, for instance, differentiation? So that's what we're going to be looking at next. So stop the video, go back, review your rules for differentiation, and let's get on with differentiation of parametric curves. So here we have a parametric curve, x equal to t, y equal to e to the t. And the question we want to know is, what is dy dx? Now that's an interesting question. What is dy dx? Well, y is a function of t. x is a function of t. So dy dx is nothing more than dy dt times dt dx, which we can write as dy dt all over dx dt. Think about that very carefully. So now, what is dy dt? Dy dt is just e to the t, so practice your differentiation. What is dx dt? That's just 1. So dy dx is nothing more than e to the t. And if t is just x, then dy dx is just e to the x. Okay, now I want to test this another way. So this formula is very important, or even this one. But what if we wrote y as a function of x? Because if I look at these two, that tells me that y is e to the x. And so straight away, dy dx is nothing more than ddx of e to the x. And that's e to the x, which is exactly what we had. But the point here is the following. We cannot always write y as a function of x. So if we can't write y as a function of x explicitly, then we got to use that rule for the derivative. Let me just write that out. So for a parametric curve, dy dx is equal to dy dt all over dx dt. Something you should know. Perfect. Let's try another example. Okay, we have a parametric curve here, x equal to t squared, y equal to t cubed minus 3t. And what we want is dy dx. But in order to get dy dx, we need dy dt divided by dx dt. So do that slowly. Do it in parts. So if I get x equal to t squared, then dx dt is 2t. If y is equal to t cubed minus 3, right neatly, then it tells me that dy dt is 3t squared minus 3. And you just put that into the formula. Dy dt is 3t squared minus 3, and dx dt is 2t, and that's your answer. Sorted out. Perfect. Beautiful. Simple. Oh, okay. What is this? Find the tangent. Tangent. The moment I see the word tangent, that calls me that y is equal to mx plus c. That's the equation of the tangent, right? Straight line general equation. But it's a tangent to the curve x equal to t squared minus 2t, and y is equal to t cubed minus 3t. So the trick here is to actually find that gradient, and that gradient m, you know, has to be dy dx, and you'd have already seen it. It's dy dt all over dx dt. We're experts now. What is dy dt? Have a look at that. That is nothing more than 3t squared minus 3. And what is dx dt? It's 2t minus 2. But it's a t equal to minus 2. So now we're going to evaluate that slope, because the slope is going to be at a point. So at t equal to minus 2, it'll be 3 into minus 2 squared. I'm evaluating here. Minus 3 all over 2 into minus 2 minus 2. Minus 2 squared is 4. 4 3 is a 12. 12 minus 3 is 9. That went very quickly. Minus 4 and minus 2 is minus 6. 3 and 2. So the gradient at t equal to minus 2 for that function is minus 3 over 2. So the tangent has equation minus 3 over 2x plus c. Whoa! Now we need to find c. How do we do that? Well, in school, if you remember, or way back in time, is that if we need c, we need a x value and a y value. So where do we obtain the x value and y value? Come. Think about that very carefully. Well, we do have x equal to t squared minus 2t. But we need to see what's happening at minus 2. So that becomes minus 2 squared minus 2 into minus 2. So you're going to get this, that's 4 and 4, so x is going to be 8. And what is the y value? The y value is going to be minus 2 cubed minus 3 into minus 2. Minus 2 cubed is minus 8, and then you got plus 6. So minus 8 plus 6 is minus 2. And no prizes for guessing. When y is minus 2, minus 3 over 2, and x is 8, we can solve for c. So that's 2 goes in 8 4 times, that's minus 12, goes on the other side. Minus 2 plus 12, c is 10. And finally, we end up with the equation of the tangent as minus 3 over 2x. c, you notice here, is 10. And there's your 2 marks. Pretty straightforward. So quick recap. So when you see the word tangent, you can write down y equal to mx plus c, because tangent's a straight line. We need to determine m, we need to determine c. M is nothing more than dy dx. Parametric curve, so we use the formula for gradient, dy dt over dx dt. Dy dt, do it slowly, is 3t squared minus 3. Dx dt is 2t minus 2. But we've got to specify at a particular point. So when t is minus 2, the gradient now becomes minus 3 over 2. Substitute in the equation for the tangent, which is a straight line, you realize we need to find c. Just like way back in time when you were much younger, in order to solve for c, you need an x value and a y value. Yeah, we got x is t squared minus 2t. We got y is t cubed minus 3t. So what is x and y doing at t equal to minus 2? We just show that x is 8 and y is minus 2. Once we got the ordered pair x, y, 8 minus 2, dump that into the equation of the tangent, find c, and you finally write down the equation. And everyone's happy in the universe. Awesome stuff, guys. Please stop, review, plot the curves, practice the differentiation, and also review your work on tangent lines. Sweet. See you on the other side of 10, whatever that means. Hey, 10. Cool stuff, man.